Okay, in this next video, we're going to talk about the concept of formal charges and how that relates to Lewis structures. Okay, so the formal charge on an atom is the charge that that atom would have if all the electrons in the molecule were shared equally. Now, of course, we know because of electronegativity that's not true, but formal charges are still really useful for showing us where or what regions of the molecule are electron rich, meaning they have extra electron density, and what regions of the molecule are electron poor, meaning they have reduced electron density. And so to calculate the formal charge, we take the valence electrons and then compare that to the number of electrons that that atom quote-unquote owns in the molecule. And we think of the electrons that it owns are, it gets all of the lone pair electrons to itself, and then we get half the bonding electrons. Now, another important feature of formal charges, so when we calculate the formal charges, we'll calculate the formal charge on each atom in the molecule or the ion, and the sum of the formal charges on all those atoms has to add up to the total charge on the molecule or the ion. So for example, if we have a neutral molecule, when we add up all the formal charges, they have to add up to 0. If I have something like sulfate, a -2 ion, and I add up the formal charges on all the atoms, they have to add up to the charge on the ion. In the case of sulfate, they'd have to add up to be -2. So the formula that I have presented here for calculating the formal charge is a little bit different to the one in the book. It works out to being the same. I've just sort of written it differently. To calculate the formal charge, we take the valence electrons, and then if you look at the formula in the book, it says, add up all the lone pair electrons and half the bonding electrons, and you subtract that from the valence electrons, and it'll give you the formal charge. And that's absolutely correct, and that's the way that I used to do it. But I saw Dr. Pennington covering this topic, and I like the form that he used. He says just add up the balls and sticks. Right, so let's look at an example for carbon dioxide. So I'll go ahead and draw the Lewis structure. So this is the Lewis structure for carbon dioxide. So if we were asked to calculate the formal charges, we have to calculate the formal charge on both of the oxygens and the carbon. So for this oxygen, we're going to do the calculation over here on the right. So the formal charge is going to be how many valence electrons an oxygen normally has. And so if we look at the periodic table, oxygen is in the 6th column, so it has 6 valence electrons. And then we subtract from that the balls and the sticks connected to that oxygen. And so we have 1, 2, 3, 4 balls, 2 sticks. So 6 minus 6, the formal charge on that oxygen is 0. All right, if we do the same thing for the carbon, I'll do the carbon in blue. So the formal charge is the number of valence electrons in carbon, so that would be 4, minus, add up all the balls and sticks. It has no balls, 4 sticks. 4 minus 4, the formal charge is 0. All right, and then if we do this last green oxygen, I think we're going to see it's going to be identical to the red oxygen. The formal charge, again, oxygen normally has 6 valence electrons. 4 balls, 2 sticks, add up to 6. So the formal charge on all 3 atoms is 0. Now if I add up those formal charges, 0 plus 0 plus 0 is of course 0, and since carbon dioxide is a neutral molecule, that's good. The formal charges in that case should add up to be 0. Okay, let's look at 2 more examples. So I have the nitrate ion and the cyanide ion. Let's do nitrate first. So let's start with these 2 oxygens. Right, and I'm going to do them together because they're the same. They both have 3 lone pairs and 1 bond. So the formal charge should be the same. So for those, the formal charge is, again, oxygen has 6 valence electrons, minus. So in both of those cases, there are 6 balls, 1 stick, so 6 plus 1 is 7. So those 2 red oxygens, the formal charge is -1. All right, if we look at the other oxygen, we'll make that one blue. So the formal charge on that oxygen is going to be 6 again, minus Now we have 4 balls, 2 sticks, so that's 6. So the formal charge on that oxygen is 0. And then we'll make the nitrogen green. And so the formal charge on that nitrogen normally has 5 valence electrons. Now there are no balls and 4 sticks. So that gives us a positive 1 for the formal charge on that nitrogen. And if we check, right, so I have 2 negatives 1s and a positive 1, so when I add, and a 0, and so when I add up those formal charges, I get negative 1, and in fact, the formal charge on a nitrate ion is negative 1, so that check worked out. Alright, let's finish up with the cyanide ion. So we'll do carbon first. And so carbon would normally have 4 valence electrons. It has 2 balls and 3 sticks, so that's 5. So the formal charge on that carbon is minus 1. And then we'll do the nitrogen in green. The formal charge is, nitrogen normally has 5 valence electrons, minus, now we have 2 balls and 3 sticks, so that's 5. So the formal charge on that nitrogen is 0. So we'll put a 0 here, put the negative 1 for that carbon. And again, the 2 formal charges add up to be the total charge on the cyanide ion, which is good. And so this also shows some of the utility of formal charges. If I just gave you this Lewis structure for cyanide, and I asked you to predict which side of the molecule was going to be more negative than the other, based on electronegativities, because nitrogen is more electronegative than carbon, we might have said that the nitrogen end of the cyanide ion is negative. But in fact, the formal charges tell us that's not the case. So we can't just look at electronegativity. Formal charges are useful, right? They tell me because the carbon is negative 1, that's where we have a buildup of electron density. And so in this case, actually, the carbon end of the cyanide ion is going to be the negative end. And so you can see the usefulness of formal charges. They tell us what regions of the molecule are going to tend to be negative and what are going to be positive. And so we can use that along with electronegativity when we're considering the electron structure of molecules.